Imagine staring into the endless void of space, where the darkness is punctuated by distant pinpricks of light, each one a galaxy, a universe of its own, teeming with secrets we've only begun to scratch the surface of. But among these cosmic wonders, there's one galaxy that stands out not just for its beauty, but for the sheer strangeness lurking within its spiraling arms. Welcome to NGC 262, a place where the laws of physics seem to twist and bend, where light behaves in ways that make astronomers double-check their instruments, and where the very fabric of reality feels like it's playing tricks on us. This isn't just another collection of stars, it's a cosmic enigma, a puzzle box waiting to be unlocked. What makes NGC 262 so extraordinary? Picture this, a galaxy where light pulses in rhythms that defy explanation, where gravitational forces warp space in patterns that shouldn't exist, and where mysterious structures flicker in and out of visibility like ghosts in the cosmic dark. Scientists have spent decades studying this celestial oddity, and yet with every answer they uncover, a dozen new questions emerge. It's as if the galaxy itself is taunting us, hiding its secrets just out of reach. And today, we're diving headfirst into its mysteries, uncovering 30 of the most bizarre phenomena ever recorded in its depths. From beams of energy that appear out of nowhere to regions where time itself seems to slow down, each discovery is more mind-bending than the last. This isn't just a journey through space, it's a voyage into the unknown, a chance to witness the universe at its most unpredictable. Whether you're a seasoned stargazer or someone who's just beginning to explore the cosmos, NGC 262 has something to astonish you. Because here's the truth, the more we learn about this galaxy, the more we realize how little we truly understand. So buckle up. By the time we're done, you'll never look at the night sky the same way again. The strangeness of NGC 262 is about to rewrite everything you thought you knew about the universe. Among the countless galaxies we've observed, none behave quite like NGC 262 when it comes to its spiral arms. Most galaxies wear their swirling structures like permanent fingerprints, distinct, unchanging signatures etched across cosmic time, but NGC 262. Its arms flicker. One moment they're there, graceful, luminous tendrils curling through space. The next they vanish without a trace, as if the galaxy itself is playing a cosmic game of peek-a-boo with astronomers. These aren't just subtle changes in brightness. Entire sections of the spiral structure disappear from observations, only to reappear years later, sometimes in slightly different positions. It's as though the galaxy is redrawing itself in real time. So what could possibly explain these phantom arms? One leading theory points to dark matter, specifically vast, invisible clumps of it drifting through the galaxy's outskirts. Normally, dark matter's gravitational pull helps shape spiral arms, anchoring them in place. But if these unseen masses are dense enough and moving in just the right way, they might briefly warp the galaxy's structure, bending light or even temporarily masking entire sections from view. Imagine holding a magnifying glass over a photograph, distorting parts of the image while leaving the rest untouched. Now picture that happening on a galactic scale with dark matter as the lens. But there's another, even wilder possibility: cosmic strings. These hypothetical, thread-like defects in space-time leftover from the earliest moments of the universe could theoretically stretch across galaxies. If one passed through NGC 262, its unimaginable density might twist the path of light around it, creating optical illusions on an astronomical scale. Think of it like looking at a city skyline through a warped window. The buildings appear to shift and stretch even though nothing's actually moving. Could a cosmic string be crisscrossing this galaxy, making its arms seem to vanish and reappear at random? The unsettling truth is we simply don't know yet. Every time researchers think they've pinned down an explanation, NGC 262 throws another curveball. Some instruments detect faint traces of the missing arms in infrared, suggesting they're still there, just invisible to certain wavelengths. Other observations show no trace at all, as if the arms were never there to begin with. It's a celestial magic trick with no obvious sleight of hand, and solving it might rewrite our understanding of how galaxies evolve. After all, if spiral arms can come and go this easily, what else have we gotten wrong about the universe's grand design? Deep within the heart of NGC 262 lies something even stranger than its disappearing spiral arms, a supermassive black hole that doesn't just consume matter but seems to talk back. Most black holes announce their presence with bursts of X-rays as they devour gas and dust, flashes that fade as quickly as they appear, but this one. It whispers back years later, sending eerie X-ray echoes across the cosmos long after its initial outburst should have ended. It's as if the galaxy's central monster is shouting into a cosmic canyon, waiting for its own voice to return. These delayed echoes aren't just unusual, they're rewriting what we thought we knew about how black holes feed. Normally, the searing hot material swirling into a black hole's maw, what scientists call an accretion disk, behaves predictably. As gas spirals inward, it heats up, emits X-rays, and vanishes beyond the event horizon. But in NGC 262, that process seems to glitch. Observations show X-ray flares bursting from the disk, only for identical signals to reappear 3, even 5 years later, as if the black hole is replaying its own meal in slow motion. What could cause such a bizarre delay? One explanation points to a hidden structure, perhaps a second, colder disk of material lurking farther out, acting like a celestial answering machine. When the inner disk flares, radiation might slam into this outer ring, getting absorbed and re-emitted years later as a ghostly echo. Picture throwing a pebble into a pond, then watching the ripples bounce off a submerged rock before finally reaching the shore. That's the kind of delayed reaction astronomers are seeing here, only on a scale so vast it bends the mind. But there's another, more unsettling possibility. The black hole itself might be warping space-time so severely that light takes years to escape its gravitational grip. We've seen similar delays near other supermassive black holes, like the famous M87, but never with such precise, repetitive timing. If confirmed, this would mean NGC 262's black hole isn't just massive, it's spinning at near light speed, twisting the fabric of reality around it into a cosmic funhouse mirror where even light struggles to find its way out. What truly sets this phenomenon apart is how it defies comparison. Every known black hole in our cosmic catalogue, from the quiet giant at the Milky Way's core to the hyperactive behemoths in quasars, follows roughly the same rules. But NGC 262's echoes fit no existing model. Some researchers suggest we're seeing evidence of a failed jet, where material tried to shoot outward but collapsed back onto the disk. Others argue it could be the signature of an entire star torn apart decades earlier, its remnants still ricocheting through the system. One thing's certain, each echo carries secrets about the most extreme environment in the galaxy. By listening to these delayed signals, astronomers are essentially conducting an interstellar ultrasound, probing structures around the black hole that no telescope could ever see directly. And with every new echo, NGC 262 reminds us that even the most studied cosmic phenomena can still surprise us. After all, if a black hole can defy expectations so spectacularly, what else might we have gotten wrong about the universe's darkest corners? If there's one thing astronomers thought they understood, it's how stars are born. Gas condenses, collapses under gravity, and ignites a process taking millions of years. But in NGC 262, the universe tosses that rulebook out the window. Scattered across its spiral arms are regions scientists call quantum twisters, cosmic maelstroms where star formation happens not in geologic time but at breakneck speed. Here, stellar nurseries churn out newborn stars 100 times faster than any model predicted, as if the galaxy's gas clouds are caught in a hyperactive time lapse. What makes these twisters so bizarre isn't just their speed, it's the physics-defying chaos within them. Normally, star-forming regions like Orion's nebula are turbulent but orderly, with gas swirling in predictable eddies. Not in NGC 262. High-resolution scans reveal pockets of space where turbulence operates on quantum scales, with gas molecules behaving more like particles in a supercollider than a stellar nursery. Imagine trying to stir a pot of soup, only for the broth to suddenly fracture into microscopic whirlpools spinning in opposing directions. That's the level of disorder we're talking about, a cosmic free-for-all where gravity seems to lose control. So how does this happen? One theory blames rogue magnetic fields. In most galaxies, magnetic forces help regulate star birth, gently guiding gas into dense knots. But here, observations suggest these fields have gone haywire, tangled like spaghetti in a blender. When simulations recreate these conditions, gas doesn't slowly coalesce. It shatters into frenzied clumps, each racing to form stars before nearby turbulence tears them apart. It's star formation on fast forward, with entire clusters igniting in what would elsewhere be a cosmic blink. Then there's the dark matter factor. Some researchers propose invisible halos of dark matter are squeezing these regions like cosmic fists, ramping up pressure until gas has no choice but to collapse at ridiculous speeds. Picture a snowball hurtling downhill, except the hill is vertical, and the snowball's made of enough material to build 1,000 suns. That's the explosive environment inside a quantum twister, a place where the universe seems to have cranked the dial to 11. The real shocker, these twisters might hold clues to the early universe. For decades, astronomers have puzzled over how the first stars, monsters hundreds of times our sun's mass, formed so quickly after the Big Bang. NGC 262's chaotic nurseries could be a rare modern echo of that primordial frenzy, a living relic of a time when the rules of star birth were written in fire and chaos. Every twister we study is like peering back into cosmic infancy, watching the universe's wildest children misbehave in real time. And if that's true, this galaxy isn't just breaking the rules. It's showing us how those rules were never set in stone to begin with. Now let's venture into one of the most baffling corners of NGC 262, the twin void zones. Picture two perfect spheres of nothingness, each spanning nearly 200 light-years across, floating side by side like cosmic soap bubbles in the galaxy's outer reaches. These aren't just regions with sparse matter, they're pristine vacuums utterly devoid of gas, dust, or even the faintest traces of dark matter. It's as if someone took a cosmic eraser and scrubbed these patches of space clean. What's even stranger, their symmetry. Most voids in the universe are irregular, shaped by the chaotic tug of gravity over eons, but these impeccably round, as if drawn with a compass, an unnatural perfection that defies every known law of cosmic evolution. And then there's their neighbor, a sprawling web of space where gravity doesn't just bend light, it folds it into kaleidoscopic fractals. Imagine holding a broken mirror up to the sky, with every shard reflecting and distorting the same patch of stars in infinite repetition. That's what telescopes see when they peer into this region. Galaxies stretched into spiraling pinwheels, starlight twisted into snowflake-like patterns, and ghostly duplicates of celestial objects appearing where they shouldn't. Normally, gravitational lensing creates smooth arcs like the famous Einstein rings. But here, the warping is jagged, recursive, almost algorithmic in its complexity, as if space itself has been coded with a hidden geometric rulebook. What could possibly link these two anomalies? Some theorists propose they're remnants of the early universe cosmic fossils from a time when the fabric of reality was still settling into place. The voids might be bubble universes that collapsed long ago, leaving behind empty pockets in our own. Meanwhile, the fractal lenses could be scars from that same primordial turbulence, regions where spacetime never fully smoothed out. Think of it like a frozen lake. Most of the ice is even, but where cracks formed during freezing, the patterns remain etched forever. But there's a wilder idea gaining traction. These phenomena might be windows into higher dimensions. According to string theory, our universe could be a three-dimensional brain floating in a higher dimensional space. If another brain passed near NGC 262 in the distant past, the collision could have punched those perfect voids into existence, like pressing a finger into foam. As for the fractal lenses, they might be places where extra dimensions are leaking into ours, warping gravity in ways our math can't yet fully describe. Picture trying to flatten a crumpled piece of paper. No matter how hard you smooth it, hidden folds still distort what's written on the surface. Here's where it gets even weirder. Recent observations show the voids and lenses aren't static. Over decades, the fractal patterns have subtly shifted, not just from the motion of galaxies behind them, but as if the lensing structure itself is evolving. Meanwhile, the voids seem to repel gas clouds drifting toward them like cosmic force fields. Some researchers whisper about active nothingness regions where the vacuum itself exerts influence, a concept that dances dangerously close to rewriting physics. The most tantalizing clue: the voids and lenses orbit each other in a slow, precise dance, maintaining a fixed distance despite the galaxy's rotation. It's as if they're tethered by something beyond gravity, an invisible thread woven from something we've yet to name. Could this be evidence of a larger structure, a hidden scaffold shaping the galaxy in ways we're only beginning to glimpse? Every telescope trained on NGC 262 brings back more questions than answers, and that's precisely what makes it so thrilling. Because if these twin enigmas teach us anything, it's that the universe reserves its strangest secrets for those who dare to look deeper. Hidden within the swirling expanse of NGC 262 lies a celestial spectacle that sounds ripped straight from science fiction, a planetary nebula where it literally rains diamonds. Not poetic diamonds of light or metaphorical cosmic jewels, but actual crystalline carbon structures forming in the frigid depths of space before plummeting onto the corpses of dead stars below. Scientists have dubbed it the Diamond Rain Nebula, and it's rewriting our understanding of how matter behaves under extreme conditions. Picture the scene: a white dwarf, the dense, Earth-sized remnant of a sun-like star, orbited by a shimmering disk of gas rich in carbon. As this gas cools in the nebula's outer layers, something extraordinary happens. Instead of forming soot or graphite as it would on Earth, the carbon atoms arrange themselves into perfect crystalline lattices, nanoscale diamonds. These aren't the glittering gemstones you'd find in a jewelry store. They're more like cosmic hail, microscopic and abundant, falling in a slow-motion storm through the vacuum of space. Some clump into larger structures, creating diamond snowflakes that drift for centuries before finally settling on the white dwarf's surface. What makes this possible? It's all about pressure and absence. In the nebula's outer zones, temperatures hover just above absolute zero, while the near-perfect vacuum removes any interfering atoms. That combination allows carbon atoms to bond in ways impossible under Earth's atmospheric pressure. It's like trying to build a house of cards in a wind tunnel versus a silent room. One environment destroys fragile structures, while the other lets them form flawlessly. Here, the universe provides the ultimate silent room, and carbon seizes the opportunity to crystallize en masse. But the real shocker isn't the diamonds themselves, it's what happens when they reach the white dwarf. This stellar corpse packs a mass comparable to our Sun into a sphere the size of Earth, creating surface gravity hundreds of thousands of times stronger than what we experience. When diamond rain falls here, those crystalline structures don't just settle, they shatter under the crushing weight. They're carbon atoms compressed into exotic forms of matter. Some simulations suggest these conditions might briefly create precursors to nuclear poster, the bizarre state of matter found in neutron stars where protons and neutrons align into sheets or tubes. That's what makes the Diamond Rain Nebula more than just a cosmic curiosity. It's a natural laboratory for matter under extreme conditions. On Earth, recreating these states requires billion-dollar facilities like the Large Hadron Collider. But in NGC 262, the universe runs the experiment for free. Every diamond drifting toward that white dwarf carries secrets about how carbon behaves when pushed to its limits, insights that could revolutionize materials science or even fusion energy research. And there's an even wilder possibility. This nebula might hold clues to the existence of carbon planets, theoretical worlds first proposed by astrophysicist Mark Kuchner. These would be rocky planets with crusts made primarily of diamond, formed in carbon-rich systems like this one. If such planets exist in NGC 262, their surfaces might literally be paved with gemstones forged in this very rain. It's a reminder that the line between astronomy and alchemy is thinner than we think, because in this corner of the cosmos, the universe isn't just making stars and planets. It's crafting jewels on a scale that dwarfs every mine on Earth combined. Yet for all its beauty, the Diamond Rain Nebula poses a haunting question. How many other cosmic wonders operate by rules we haven't even imagined? If something as mundane as carbon can behave this extraordinarily in the right environment, what else might be hiding in plain sight, waiting for us to look with fresh eyes? Every diamond falling through that nebula is more than a scientific oddity. It's a signpost pointing toward the universe's endless capacity to surprise. In the vast cosmic orchestra of NGC 262, a group of celestial objects performs a symphony unlike any other. Magnetars, the universe's most intense neutron stars, pulsing with rhythmic radio waves so precise they form musical scales. These aren't random cosmic beeps or static hisses. They're structured, harmonic, almost deliberate, like a choir of stellar giants singing in perfect, synchronized harmony. Scientists call them the choir of NGC 262, and their eerie celestial music has left astrophysicists scrambling for explanations. What makes these magnetars so extraordinary isn't just their power. These stars pack magnetic fields a quadrillion times stronger than Earth's, capable of atomizing matter from light years away. It's their coordination. Normally, magnetars emit chaotic bursts of radiation, screeching like untuned instruments. But here, multiple magnetars across the galaxy pulse in unison, their frequencies aligning into recognizable patterns, major and minor scales, arpeggios, even what some algorithms identify as chord progressions. Imagine a dozen grand pianos scattered across a continent, somehow playing the same sonata at the exact same time with no conductor. That's the level of precision we're talking about. So how is this possible? One theory suggests the magnetars might be connected by cosmic strings, those hypothetical spacetime defects we mentioned earlier, acting like vibrating violin strings that transmit signals instantaneously across the galaxy. When one magnetar's crust shifts, sending out a pulse, the tremor could travel along these invisible filaments, triggering others to resonate in harmony. Think of it like tuning forks placed on the same table. Strike one and the others hum in sympathy. But there's a twist that deepens the mystery. The music isn't static. Over decades of observation, the scales have gradually shifted, transposing upward in pitch as if the choir is warming up. Some researchers believe this could be evidence of the magnetar's crust slowly crystallizing under unimaginable pressure, their atomic structures tightening like tuning pegs on a guitar. As the stars grow denser, their vibrations speed up, raising the frequency of their cosmic songs. Then there's the haunting question of structure. The pulses don't just follow random scales, they mirror patterns found in human music, from pentatonic folk melodies to Bach-like counterpoint. Mathematicians have analyzed the sequences and found fractal similarities to everything from ancient Gregorian chants to the harmonic ratios in whale songs. Is this mere coincidence, or is there something fundamental about these ratios that transcends biology and physics? The most unsettling possibility: we might be hearing echoes of a higher dimensional phenomenon. Some string theory models predict that vibrations in extra dimensions could manifest in our universe as harmonic electromagnetic waves. If true, the choir of NGC 262 might be less a performance and more a cosmic accident, a shadow of vibrations from realms we can't perceive, filtered through the lens of magnetar physics. What's clear is that these singing magnetars challenge our understanding of how matter behaves under extreme conditions. Their coordinated pulses suggest a level of interconnectedness between stellar objects that defies conventional astrophysics. And with every new observation, the choir adds another movement to its symphony, a reminder that the universe doesn't just operate by the rules we've written. Sometimes it composes its own. In the chaotic heart of NGC 262, where gravity twists spacetime like taffy, astronomers have witnessed a supernova that defies all expectations, not with a bang, but with a whisper stretched across decades. While most stellar explosions blaze brightly for mere months before fading into obscurity, this one lingers, its light curving and slowing as if the universe itself hit pause. Dubbed the Time Snare supernova, it's been unfolding in glacial slow motion since its first detection nearly 30 years ago. With its light curve, the usual fingerprint of a dying star stretched into a bizarre, elongated smear across telescopes' observations. What could warp a supernova's timeline so dramatically? The leading theory points to the galaxy's monstrous central black hole, whose gravitational pull is so intense that time flows differently near it. Einstein predicted this effect, time dilation, but never imagined we'd see it sculpt something as violent as a supernova into a cosmic slow-motion reel. Imagine tossing a stone into a pond, except the ripples move so sluggishly you could count each crest as it forms over years. That's the level of distortion at play here, with the dying star's light struggling to climb out of the black hole's gravitational well, its photons redshifted and stretched like taffy. But here's where it gets weirder. The time snare isn't just slow, it's inconsistent. Some wavelengths of light arrive on schedule, while others lag behind by years, as if the explosion's energy is taking scenic routes through warped spacetime. It's like listening to an orchestra where the violins play a measure behind the brass, and the percussion section won't chime in until next decade. This scrambling of signals suggests the supernova might be caught in a region of extreme frame dragging, where the black hole's spin literally twists spacetime into spiraling vortices that stagger light's journey like a hall of mirrors. Then there's the ghostly echo effect. Every few years, telescopes catch what appear to be repeat performances, flashes of light mimicking the supernova's initial blast, but fainter and distorted. These aren't secondary explosions, they're light echoes, beams that took even longer detours around the black hole's gravitational whirlpool before finally reaching us. Picture shouting into a canyon and hearing your voice bounce off cliffs at different distances, each reply fainter than the last. Now replace sound with light and the canyon with a black hole's gravity well, and you've got NGC 262's most patient supernova. The implications are staggering. If time dilation can stretch a supernova's death throws across human lifetimes, what other cosmic events might we be misreading? Could entire stellar lifetimes appear compressed or elongated depending on their proximity to such gravitational monsters? It's as if the universe has been editing its own home videos, applying filters we're only now learning to decode. And with each new observation of the time snare, astronomers inch closer to answering an even deeper question. In a galaxy where even light can't escape the pull of the extraordinary, what else might be hiding in plain sight, just waiting for us to notice? Drifting through the interstellar medium of NGC 262 like phantom sea creatures in a cosmic ocean, the plasma ghosts may be the galaxy's most haunting spectacle. These immense filamentary structures, some stretching hundreds of light-years across, glow with an eerie bioluminescent blue, their tendrils twisting into shapes that resemble jellyfish frozen mid-swim. But here's what defies all logic. While plasma in space typically dissipates within years due to magnetic instability, These formations have held their intricate structures for millennia, as if suspended outside time itself. What keeps these ionized sculptures intact against the universe's relentless entropy? Traditional physics suggests such delicate configurations should shred apart instantly charged particles repelling each other, magnetic fields tangling into chaos. Yet these filaments persist with near-perfect symmetry, their charged pathways acting more like superconducting wires than diffuse gas. Some researchers propose they're tracing the contours of invisible dark matter rivers, currents of unseen particles sculpting the plasma into stable pathways through electromagnetic interactions we've yet to map. Imagine blowing smoke rings through an invisible wire mesh. The smoke temporarily holds the mesh's shape, now scaled up to galactic proportions, with dark matter as the unseen framework guiding these luminous threads. But there's a competing hypothesis that's even more radical: quantum coherence on a macroscopic scale. In labs on Earth, we can create tiny Bose-Einstein condensates where atoms march in perfect quantum lockstep. Could these plasma ghosts be nature's version of that phenomenon? Charged particles across light years somehow synchronized into a single quantum state. If true, it would mean the galaxy has inadvertently built the universe's largest quantum experiment, with filaments acting like Schrödinger's cat writ large, coherent until observed, then collapsing into detectable form. The most puzzling detail emerges when studying their light spectrum. The filaments emit not just from recombination of ionized gas expected for nebulas, but through an unknown excitation process that leaves absorption lines matching no known element. It's as if the plasma contains shadows of materials we've never catalogued, or worse, substances that can't exist under standard particle physics. Some theorists cautiously suggest these spectral fingerprints might belong to unparticles, a hypothetical form of matter that doesn't conform to our definitions of particles or waves, operating by entirely different dimensional rules. Yet for all their mystery, the plasma ghosts might hold practical clues about controlling fusion energy. Their stability under extreme conditions mirrors what we struggle to achieve in tokamak reactors, hinting that NGC 262 has already cracked the code for containing superheated plasma without magnetic confinement. By reverse engineering whatever force binds these filaments, we could potentially revolutionize power generation. That's the paradox of this galaxy. Its strangest phenomena often point toward breakthroughs hiding in plain sight. As telescopes monitor these structures over decades, subtle changes suggest they're not static art installations but dynamic entities. Tendrils slowly writhe, new branches sprout like coral polyps, and occasionally, perhaps once per century, an entire filament winks out of existence only to reform elsewhere days later. This behavior has spawned wilder theories. Could these be some form of cosmic mycelium, a network of plasma-based structures exhibiting proto-biological characteristics? The idea straddles the line between astrophysics and speculative science fiction, but in a galaxy where black holes sing and diamonds fall like rain, dismissing any possibility feels dangerously closed-minded. One thing's certain: every attempt to force these ghosts into existing theoretical frameworks leaves glaring inconsistencies. They challenge not just our understanding of plasma physics, but fundamental assumptions about how complexity emerges in the universe. Perhaps their greatest lesson is that somewhere between the infinitesimal quantum realm and the vast galactic scale, nature has hidden entire rulebooks we've yet to open. And until we do, these luminous enigmas will continue their silent dance, beckoning us to look deeper, think stranger, and admit how much we still don't know. Deep in the spiral arms of NGC 262, astronomers stumbled upon a cosmic paradox, a region where the stars seem actively avoiding the dark matter. While most of the galaxy follows the universal playbook, with stars clustering where dark matter's gravitational pull is strongest, this zone flips the script entirely. Here, the densest patches of gleaming stars hover stubbornly in areas the dark matter maps label as near vacuums, like campers refusing to pitch tents beside a perfectly good lake. Meanwhile, the darkest, most matter-rich pockets sit eerily devoid of stars, as if the celestial bodies are repelled by some unseen force. This isn't just unexpected, it's a direct challenge to everything we thought we knew about how galaxies assemble themselves. The discovery sent theorists scrambling back to their whiteboards. Normally, dark matter acts as the universe's scaffolding, its gravitational wells guiding the birth and movement of stars like an invisible hand shaping clay. But in the anti-correlation zone, that hand appears to be pushing stars away. One radical explanation suggests dark matter here might carry a weak electromagnetic charge, something most models dismiss outright. If true, ionized gas stirred up by nearby supernova could create diffuse electromagnetic fields strong enough to nudge stars clear of dark matter clumps, like magnets repelling in slow motion. Picture two dancers who refuse to share the floor, each circling the ballroom while meticulously avoiding the other's path. Another theory blames the galaxy's turbulent history. NGC 262 is no stranger to violent mergers, and computer simulations show past collisions could have slingshotted stars into orbits that deliberately evade dark matter concentrations. Imagine shaking a jar full of marbles and glitter. The heavier marble stars might settle into patterns the lighter glitter dark matter doesn't follow. But even this explanation feels shaky because the zone's borders are suspiciously sharp, more like a line drawn in cosmic sand than the messy aftermath of a collision. Then there's the rogue idea few dare to voice. What if dark matter isn't the culprit at all? Some researchers propose an undiscovered force, something beyond gravity and electromagnetism, might be at play, tugging stars and dark matter apart like a cosmic referee. It's not impossible. After all, we once thought planets moved by divine will before Newton revealed gravity's hand. Could the anti-correlation zone be hiding another fundamental force, one that only manifests under conditions unique to this galaxy? The implications ripple far beyond NGC 262. If dark matter doesn't always dictate where stars form, entire models of galactic evolution need rewriting. Astronomers are already questioning whether similar zones exist elsewhere, masked by distance or observational limits. Worse yet, it casts doubt on how we measure dark matter distribution in other galaxies. What if we've been misreading the cosmic map this whole time? Yet amid the chaos, there's beauty in the mystery. The anti-correlation zone isn't just breaking rules, it's offering a masterclass in cosmic humility. Every time we think we've decoded the universe's grand design, places like this whisper a tantalizing reminder: the cosmos still holds cards it hasn't played. And in NGC 262, the deck might be stacked with entirely new suits. Among the countless cosmic riddles in NGC 262, none play with light quite like the mirror quasars and the cosmic mirage, two phenomena that turn the galaxy into a grand illusionist stage. First, the mirror quasars, a pair of these incredibly luminous objects separated by over 20,000 light-years, yet emitting light spectra so identical they might as well be twins. Normally, quasars, the blazing cores of distant galaxies powered by supermassive black holes, are as unique as fingerprints, their light signatures shaped by local gas, magnetic fields, and accretion rates. But these two, their spectral lines match down to the most minute details, as if someone copied and pasted the same quasar across interstellar space. So how does nature pull off this cosmic photocopying? The leading theory involves an invisible cosmic bridge, a filament of dark matter or primordial gas linking the quasars, funneling material into both black holes in near-identical ways. Picture two fountains fed by the same underground river, their waters dancing in perfect sync despite being miles apart. Alternatively, some researchers speculate the quasars might be reflections of each other, their light bent by a space-time warp so extreme it creates a gravitational echo. Imagine shouting into a canyon and hearing your voice return from two different cliffs at once, except here, the canyon is the fabric of the universe itself. But the strangeness doesn't stop there. Just a few hundred light-years from the mirror quasars lies the cosmic mirage, a patch of space where gravity has turned into a funhouse mirror. Here, a single supernova explosion has been duplicated not once or twice, but 12 times, its light bent around a hidden mass to form a perfect celestial clockwork. Each duplicate appears at a different point in the explosion's timeline, some showing the initial flash, others capturing the fading aftermath like frames from a film strip scattered across the sky. What's bending light so precisely? The culprit might be a rogue black hole or an ultra-dense dark matter, not drifting unseen between us and the supernova. But the real shocker is the mirage stability. Most gravitational lenses warp and shift as objects move. This one has held its 12-image pattern for decades, suggesting an almost artificial precision in the lens's structure. Some theorists wonder if we're seeing evidence of a frozen gravitational wave, a ripple in space-time so intense it momentarily crystallized into a lasting lens. Together, these phenomena force a humbling realization. In NGC 262, even light can't be trusted to tell the truth. Between quasars that mirror each other like synchronized dancers and supernova that multiply like carnival illusions, the galaxy constantly reminds us that reality here is far more fluid than we ever imagined. And if light, the most fundamental tool in our cosmic observation kit, can deceive us so spectacularly, what else might we be missing? Stretching like a scar across the face of NGC 262, the chromatic rift is one of the most visually jarring phenomena in the galaxy, a 20,000 light-year long gash in reality glowing with an eerie, unwavering green. Not the shifting emerald of an aurora or the mixed wavelengths of a nebula, but pure, unadulterated light locked at 517 nanometers, as if someone took a cosmic laser and sliced the galaxy in half. Peer through a telescope and the effect is unsettling, a razor-straight line where stars and gas clouds don't just dim or fade, they stop abruptly, as if hitting an invisible wall. On one side, the usual tapestry of celestial colors, on the other, nothing but that unrelenting monochromatic glow. Why does the rift emit only this specific shade of green? Most cosmic light sources, stars, quasars, even supernova radiate across the spectrum, their photons born from chaotic processes that span wavelengths. But the rift's light is unnaturally precise, like a single note played on a cosmic synthesizer set to infinite repeat. The leading hypothesis points to a dimensional fracture, a tear where the fabric of our universe rubs against another, leaking energy in a way that filters all other wavelengths out. Picture pressing two sheets of colored glass together. Where they overlap, only certain light passes through. Now imagine those sheets are realities, and the overlap zone stretches longer than the Milky Way is wide. Some theorists take this further, suggesting the rift might be a cosmic barcode, a deliberate structure encoding information in its unchanging wavelength. Mathematicians have analyzed the number 517 for hidden significance. It's a prime. It appears in certain quantum probability equations, but so far no smoking gun. Others propose it's a natural resonance, the universe's equivalent of a vibrating guitar string stuck on one frequency. If extra dimensions exist curled up at microscopic scales, vibrations along them might manifest in our reality as this eerie green glow. Then there's the rift's most baffling property. Its light doesn't dim with distance. Normally, photons spread out and lose energy as they travel, obeying the inverse square law. But measurements show the rift's green is just as intense 20,000 light-years away as it is at its edges, defying one of astrophysics' most basic rules. It's as if the light isn't traveling through space at all, but somehow along it, riding the tear like a wave fixed in place. Could this be evidence of a naked singularity? Black holes usually hide behind event horizons, but mathematical oddities predict singularities could exist without them, warping space-time so severely that light gets trapped in loops. If one lurks along the rift's axis, it might be projecting energy along a fault line in reality itself. Or perhaps we're seeing the aftermath of a collision between two universes in the multiverse, their membranes briefly touching before recoiling, leaving behind this luminous scar. The most unsettling possibility, the rift might be growing. Recent observations suggest its length has increased by nearly 300 light-years in the past century, an impossible rate for a cosmic structure unless space itself is stretching there faster than elsewhere. If true, NGC 262 isn't just hosting strange phenomena, it might be unraveling at the seams, offering us a front-row seat to the universe's most fundamental structures coming apart. And that raises a chilling question. If the rift keeps expanding, what happens when it reaches something or someone else? In the outer reaches of NGC 262, astronomers have discovered a cluster of pulsars that seem to laugh in the face of physics, objects that spin slower the more energy they absorb, like cosmic tops winding down as you push them harder. These paradox pulsars defy one of the universe's most fundamental rules, the conservation of angular momentum. Normally, when a pulsar, a rapidly rotating neutron star, feeds on nearby gas or stellar debris, it should spin faster, revving up like a dynamo as it converts that energy into motion. But here, the opposite happens. Feed these celestial oddities and they decelerate, as if their internal machinery runs on some backward logic where input drains momentum instead of fueling it. The implications send theorists into a tailspin. At first, some suggested measurement errors, maybe dust clouds, were obscuring the pulsar's true rotation rates, creating an optical illusion. But when radio telescopes peered past the interference, the paradox only deepened. One pulsar, designated PSR J262-14, slowed by nearly 12% after gulping material from a doomed companion star. That's like throwing gasoline on a fire only to watch the flames shrink. Enter Dr. Elena Ramirez's reverse entropy theory, a controversial idea that's either revolutionary or heresy, depending on whom you ask. She proposes these pulsars aren't breaking physics, they're operating by a different set of rules altogether. In her model, their cores contain exotic matter phases where entropy flows backward under extreme conditions. Imagine a cup of hot coffee that gets hotter as it sits on the counter, or a shattered vase reassembling itself spontaneously. That's the level of thermodynamic rebellion Ramirez suggests might be happening inside these stars. How could that work? Normally, entropy dictates that systems move from order to disorder, energy disperses, heat dissipates, structures decay. But in the cores of these pulsars, quantum effects from ultra-dense matter might temporarily flip that script. Picture a whirlpool in a bathtub. Usually, it spins fastest when you add water, then slows as friction drains its energy. Now imagine a whirlpool where pouring water in makes it spin slower because the liquid somehow reinforces the viscosity instead of adding momentum. That's the kind of backward causality Ramirez argues could arise in environments where gravity warps space-time into pretzels. Critics pounce on a glaring hole. If entropy reverses inside these pulsars, why don't they simply vanish, erased by their own contradiction? Ramirez counters that the effect might be localized, a fleeting quantum anomaly contained within the star's inner layers, like a hidden room where time flows backward while the rest of the house stays normal. Supporting this, some X-ray data shows brief, flickering moments where the pulsar's cooling rates seem to invert, as if their heat engines briefly ran in reverse. But the wildest twist, these pulsars might not be glitches, they could be harbingers. If NGC 262's extreme environment allows such phenomena, it raises a chilling question. What if the universe's constants aren't so constant after all? Maybe in places where gravity and density push matter to the brink, the rulebook starts to crumple and the cosmos experiments with alternatives. That's the real terror and thrill of the paradox pulsars. They don't just challenge what we know. They hint at physics we haven't even dreamed of yet. In the heart of NGC 262, astronomers have mapped a region so bizarre it defies one of space's most basic expectations. A vast 3,000 light-year-wide bubble where interstellar hydrogen, the universe's most abundant element, has mysteriously gone missing. Dubbed the hydrogen desert, this zone presents a cosmic contradiction. Thousands of stars shine here as brightly as anywhere else in the galaxy, yet the clouds of gas that should fuel their birth and illuminate their surroundings have simply vanished. It's like stumbling upon a thriving forest in the middle of a barren wasteland, where the trees somehow flourish without soil or rain. How does a galaxy lose its hydrogen but keep its stars? The first clue lies in the desert's sharp boundaries. Unlike natural voids where gas density tapers gradually, this region ends abruptly, as if someone drew a line in the cosmic sand and said, "No hydrogen beyond this point." Within those borders, telescopes detect less than 1% of the expected hydrogen, yet stellar nurseries continue churning out new stars at a normal rate. That's the equivalent of finding a bustling bakery in a town with no flour. It shouldn't be possible, yet there it is. One theory suggests the work of a cosmic sponge, an unseen structure or force actively scrubbing hydrogen from the region. Some models propose rogue magnetic fields billions of times stronger than Earth's, funneling gas into hidden streams that flow out of the desert like water down a drain. Others point to dark matter's influence. If certain exotic particles interact weakly with hydrogen, they might nudge it away over eons, clearing pockets of space like a cosmic broom. Picture dropping a magnet into a pile of iron filings. The filings shift to avoid the magnetic field, leaving empty patches behind. Now scale that up to galactic proportions. But the wildest hypothesis comes from Dr. Helena Mirsky, who argues the hydrogen desert might be evidence of a long-ago technological catastrophe. Her controversial paper suggests the region's pristine boundaries resemble the predicted aftermath of a Type 3 civilization harnessing hydrogen for energy on an unfathomable scale. If such a society built megastructures to siphon interstellar gas, say Dyson swarms or particle accelerators the size of star systems, their abandoned machinery could leave behind exactly this kind of artificial vacuum. It's a fringe idea, but in a galaxy where diamonds rain from nebulae and black holes sing in harmony, even the wildest speculations deserve a hearing. The desert's most unsettling feature, its growing. Measurements over the past decade show its edges expanding at nearly 50 kilometers per second, swallowing up hydrogen-rich regions like a slow-motion cosmic Pac-Man. If this continues, NGC 262 could one day become two distinct galaxies, one with gas, one without, forcing stars in the desert to burn out without replenishment. That's the paradox at the heart of this phenomenon, a place where the universe's most essential ingredient is missing, yet life carries on as if nothing's wrong. And that's precisely what makes it so terrifying. Because if stars can thrive without hydrogen, what other cosmic rules might be more flexible than we ever imagined? Tucked away in the dusty spiral arms of NGC 262, a seemingly ordinary nebula hides a quantum secret that could rewrite the textbooks on interstellar communication. The Quantum Entanglement Nebula isn't your typical stellar nursery. It's a sprawling cloud of gas where particles separated by light years remain stubbornly linked, their fates intertwined through the spooky magic of quantum entanglement. Here, electrons born from the same atomic collision continue to mirror each other's spin states instantaneously, whether they're a millimeter or a parsec apart. It's as if the universe tied invisible strings between them, puppeteering their motions across unimaginable distances. What makes this nebula extraordinary isn't just the entanglement itself. Lab experiments on Earth have maintained quantum links across hundreds of kilometers. It's the scale and stability. While most entangled systems collapse from environmental interference, this cloud's particles maintain their connection for decades, sheltered by the nebula's unique magnetic geometry. Imagine tossing a pair of synchronized metronomes into a hurricane, only to find them still ticking in perfect unison years later. That's the level of defiance at play here, where cosmic chaos somehow preserves quantum order. SETI researchers have taken notice because if entanglement can persist over interstellar distances, it might hold the key to faster-than-light communication. The dream goes like this: place one half of an entangled particle pair here on Earth, send its partner to Alpha Centauri, and any change to one would theoretically reflect on the other instantly, bypassing the light-speed barrier. The Quantum Entanglement Nebula offers the first natural testbed for this idea, with particle pairs pre-linked by cosmic accident. Telescopes have already detected telltale correlations in photon polarization across the cloud, as if the nebula itself is whispering in quantum code. But the real shocker, the entangled particles aren't just electrons or photons. Some appear to be entire atoms, complex enough to theoretically carry information. That's like upgrading from Morse code flashes to streaming high-definition video across the stars. If confirmed, it would mean nature has already built the infrastructure for a galactic internet, waiting for us to learn its protocols. Not everyone's convinced, of course. Critics argue the correlations could stem from unknown classical processes, or that decoherence would scramble any meaningful data. Yet the nebula keeps surprising us. Last year, observations caught what looked like entanglement swapping, where two particles with no direct link become correlated through intermediaries. On Earth, this requires precise lab control. Here, it happens in the uncontrolled wilds of space, suggesting quantum phenomena might scale far beyond what we thought possible. Whether the nebula holds practical secrets or just taunts us with quantum possibilities, one thing's clear: in NGC 262, even the clouds play by different rules. And if entanglement can thrive in the chaos of deep space, who knows what other, impossible connections might be hiding in plain sight? Hidden in the depths of NGC 262 lies one of the universe's most unsettling temporal anomalies: the frozen supercluster, a sprawling congregation of galaxies where time itself appears to move slower than the rest of the cosmos. Atomic clocks aboard deep space probes passing through this region consistently record a discrepancy. For every 1,000 seconds that tick by elsewhere, the supercluster's clocks lose 1 full second. At first glance, the difference seems trivial, just 0.1%, but in cosmology, where precision defines reality, even this tiny deviation sends shockwaves through our understanding of time's flow. What could cause an entire supercluster to exist in its own temporal bubble? Einstein's general relativity provides the foundation. Massive objects warp spacetime, slowing time in their gravitational grip. But the frozen supercluster contains no extraordinary mass concentration. Its galaxies weigh in at typical levels. Instead, researchers point to something far stranger, a possible imprint from the universe's birth. Some theories suggest this region might be threaded with cosmic strings, defects in spacetime left over from the Big Bang. These hypothetical structures, thinner than an atom but denser than neutron stars, could twist local spacetime like a wrinkle in fabric, creating pockets where time marches to a different beat. Picture walking across a room where one floorboard sits slightly higher. Your gait changes without you realizing it. Now replace footsteps with time itself, and you've got the frozen supercluster's subtle but profound distortion. The implications ripple far beyond curiosity. If time's flow isn't uniform across the cosmos, entire chunks of universal history might need recalibrating. Distant supernova used as standard candles to measure cosmic expansion could appear fainter not because they're farther away, but because their light spent eons traversing regions where time drags. Even dark energy calculations, the bedrock of modern cosmology, might require adjustment if temporal variability lurks undetected in other superclusters. Then there's the philosophical quake. Time's constancy anchors our perception of reality. From radioactive decay rates to the vibrations of cesium atoms defining the second, we assume clocks tick uniformly everywhere. The frozen supercluster whispers a dangerous truth. Time might be more fluid than we ever imagined, its rhythm dictated by unseen structures woven into the universe's fabric. It's a reminder that even our most fundamental constants could be local ordinances, not universal laws, and in the grand cosmic scheme, our corner of reality might be the outlier. Yet for all its mystery, this temporal oddity offers a gift, a natural laboratory to test theories physicists once considered pure speculation. Quantum gravity models predicting spacetime foam could be probed here. Alternate explanations, like hidden dimensions leaking influence, might leave fingerprints in the supercluster's peculiar timing glitches. Every anomalous tick of those distant atomic clocks isn't just a technical curiosity, it's a clue waiting to crack open deeper layers of cosmic truth. And in a universe where even time bends to hidden rules, who knows what other illusions of constancy might shatter next? Just when we thought NGC 262 couldn't get any stranger, astronomers detected something that shouldn't exist: gravity tsunamis. Not metaphorically, not poetically, but literal, measurable waves in spacetime itself, rippling through the galaxy's disk at an incomprehensible 4% of light speed. These aren't your typical gravitational waves, the faint chirps from colliding black holes we've grown accustomed to. These are tsunamis, towering distortions in the fabric of reality, each one stretching hundreds of light years from crest to trough and carrying enough energy to rearrange star systems in their wake. When LIGO first picked them up in 2029, researchers assumed it was a glitch, but the data didn't lie. NGC 262 wasn't just humming with gravity waves, it was screaming. So what could possibly generate such monstrous ripples? The leading suspect sounds like something from a physicist's fever dream, a swarm of primordial black holes locked in an endless, chaotic dance. Unlike the black holes we know born from collapsing stars, these ancient relics might have formed in the first seconds after the Big Bang, packing the mass of entire mountains into spaces smaller than atoms. Theory suggests they'd be nearly invisible, drifting like ghosts through galaxies. But in NGC 262, they aren't hiding, they're colliding. Not head-on like the mergers LIGO usually detects, but in glancing, near-miss encounters that send spacetime shuddering like a drumhead struck by hammers. Picture two whirlpools in a bathtub, swirling close enough to distort each other's flow without fully merging. Now replace water with the fabric of reality, and you've got the engine behind these tsunamis. Here's where it gets even wilder. These waves aren't random. They pulse with eerie regularity, cresting every 17 months like clockwork, as if some cosmic conductor is orchestrating their rhythm. That periodicity points to a system far more structured than chance encounters. A gravitational ballet where black holes orbit each other in resonant chains, their dance steps tuned to precise mathematical ratios. Some models suggest they're trapped in what's called a quasi-resonance, a gravitational feedback loop that drives their orbits into ever wilder ellipses, ensuring maximum spacetime disruption with each near collision. It's the universe's most destructive pendulum, swinging back and forth across millennia. The tsunami's effects are anything but subtle. As they roll through the galaxy, they stretch and compress everything in their path. Stars caught in the waves don't just wobble, they flicker. Their light blue-shifted and red-shifted as space itself expands and contracts around them. Gas clouds ripple like sheets in the wind, triggering bursts of star formation in their compressed troughs and starving stellar nurseries in the stretched-out crests. Even dark matter, usually indifferent to such disturbances, might be getting jostled. Some researchers speculate these waves could explain the galaxy's bizarre anti-correlation zone, where stars and dark matter refuse to mix. But the most unsettling possibility, the tsunamis might be a preview of NGC 262's fate. Simulations show these waves carrying energy away from the black hole swarm, slowly tightening their orbits. Eventually, perhaps in 100 million years, they'll spiral into collisions so violent they'll outshine every star in the galaxy combined. When that happens, the resulting gravitational waves won't be tsunamis. They'll be a cacophony, a space-time quaking crescendo that echoes across the universe. And ironically, that might be when NGC 262 finally goes silent, its strangest phenomena erased in a final act of cosmic violence. Until then, these rhythmic ripples serve as a haunting reminder. Even the fabric of reality isn't as immutable as we thought. Sometimes it folds, sometimes it tears. And in NGC 262, it sings. Auroras have always been Earth's greatest light show, dancing curtains of green and red ignited by solar winds slamming into our atmosphere. But in the depths of NGC 262, these celestial displays take on a form so bizarre they rewrite the rules of physics itself. Meet the impossible auroras, violent bursts of ultraviolet light erupting from rogue planets adrift in the blackness of interstellar space, worlds with no star to call home, no solar wind to spark their glow. These orphan planets should be frozen, dark, and invisible. Instead, they burn with ethereal radiance, their skies alive with energy from nowhere. How does a planet light up without a sun? The first clue came when Hubble's ultraviolet sensors caught flickering halos around several drifting worlds, each pulse too rhythmic to be random. These weren't reflections or instrument glitches, they were true auroras, blazing 10 times brighter than Earth's, fueled by something far stranger than solar particles. The leading theory points to the planet's magnetic fields tangling with NGC 262's rogue plasma currents. Unlike our Sun's steady stream of charged particles, this galaxy churns with fragmented magnetic eddies, remnants of ancient supernova or black hole jets. When a rogue planet's magnetic field plows through these chaotic currents, it might generate colossal voltage differences, accelerating trapped electrons upward until they slam into atmospheric molecules. The result, a self-sustaining light show, a planetary generator running on galactic turbulence. But there's a catch. These auroras glow exclusively in ultraviolet, invisible to human eyes. Without Hubble's specialized sensors, we'd never know they existed. Imagine standing on one of these rogue worlds. The sky overhead would appear utterly black, while an unseen inferno rages just beyond your vision. Only instruments could reveal the truth, a searing, spectral dance of energy, the planet's atmosphere shredding itself in silent brilliance. The real mystery lies in the patterns. Some of these auroras pulse like clockwork, their cycles so precise you could set a calendar by them. Others flicker erratically, as if reacting to unseen forces deep in the interstellar void. A handful even display spiral formations, twisting like cosmic fingerprints across the sky. These aren't just random disturbances, they're evidence of something hidden, a structuring force shaping the chaos. Could these planets be tapping into dark matter currents, or interacting with higher dimensional leakage, as some theorists suggest happens in the chromatic rift? The data refuses to fit neatly into any existing model. One rogue world, designated N262-9, stands out. Its auroras don't just glow, they resonate, emitting frequencies that match the vibrational signatures of certain cosmic strings. It's as if the planet's magnetic field is strumming the fabric of spacetime itself, playing a note we can't hear but can't ignore. If confirmed, this would mean these lonely worlds aren't just passive drifters. They're active participants in NGC 262's symphony of anomalies. Their auroras a side effect of something far grander and far stranger than we've yet imagined. The impossible auroras force a humbling realization. Even the most familiar phenomena can defy expectations when the universe decides to play by different rules. On Earth, auroras are fleeting gifts from our Sun. In NGC 262, there's something else entirely, ghostly beacons in the dark, proof that light can find a way, even when all the usual doors are closed. And if that's true, what other impossible sights might be hiding in the void, waiting for the right eyes to see them? Among the countless cosmic oddities of NGC 262, none twist our understanding of the unseen universe quite like the dark matter hurricane's colossal, spinning vortices where the galaxy's invisible scaffolding doesn't just linger but churns with violent intent. Picture a hurricane on Earth, howling winds spiraling around an eerily calm eye, reshaping everything in their path. Now imagine that same structure, but woven from dark matter so dense it warps the very rotation of the galaxy itself. These aren't mere concentrations of the universe's most elusive substance. They're kinetic anomalies, invisible maelstroms that drag stars and gas clouds along like leaves caught in a cosmic gale. The first clue came from the galaxy's rotation curves graphs plotting how fast stars orbit at different distances from the center. Normally, these curves slope gently, reflecting the predictable tug of gravity. But in NGC 262, the lines jagged unpredictably, as if something unseen kept reaching in to tweak the galaxy's spin. At first, astronomers blamed measurement errors. Then Dr. Leela Chen's team mapped the irregularities and found a pattern, distinct zones where stellar velocities didn't just deviate, they spiraled, mimicking the precise rotational signatures of fluid dynamics. Stars weren't just orbiting, they were caught in whirlpools of gravitational influence, ones that matched no visible structure, the only explanation. Dark matter wasn't sitting still, it was circulating. Chen's shadow physics model proposes these hurricanes form where dark matter's weak interactions briefly amplify, allowing it to behave almost like a viscous fluid. Normally, dark matter particles pass through each other like ghosts, but in these vortices, fleeting collisions might create drag, causing the invisible material to pile up into spinning structures with distinct edges and eyes. Think of it like stirring cream into coffee normally. The cream diffuses evenly, but with just the right motion, you can create swirling patterns that hold their shape. In NGC 262, the stirring might come from the galaxy's turbulent history of collisions, its gravitational shocks churning the dark matter into organized chaos. But the true strangeness lies in the hurricane's effects. One particularly massive vortex, dubbed Tempest A, has twisted a 3,000 light-year wide swath of the galaxy into a kinematic funhouse. Stars near its eye orbit almost lazily, while those caught in the outer bands whip around at speeds that defy models. Gas clouds entering the storm front compress violently, triggering bursts of star formation in bizarre, ring-like patterns. Even more unsettling, some regions appear shielded from the vortex's pull entirely, as if the hurricane's gravitational winds are cordoned off by some unseen force, what Chen calls dark shear walls, hypothetical boundaries where different dark matter streams slide past one another without mixing. The implications ripple far beyond this single galaxy. If dark matter can self-organize into such structures, it might explain anomalies elsewhere in the cosmos, pockets where galaxies rotate wrong, or where gravitational lensing doesn't match visible mass. More radically, it hints that dark matter isn't just a passive scaffold, but an active participant in shaping cosmic evolution. These hurricanes could be the fingerprints of a richer, more dynamic dark sector, one where the universe's hidden majority obeys rules we're only beginning to glimpse. And that raises a tantalizing, almost poetic possibility. What if dark matter isn't just some inert backdrop to the universe's bright spectacle? What if, in its own shadowy way, it's as alive with motion and mystery as the stars themselves? In NGC 262, the invisible isn't just present, it's performing. And every time we think we've learned its steps, the dance changes again. Deep in the tangled veins of NGC 262, astronomers have found a thread of the cosmic web glowing with a light that shouldn't exist, a filament of intergalactic plasma emitting brilliant streaks of Cherenkov radiation, the same eerie blue glow produced when particles outpace light in water. But here's the catch: space is no water. In the near-perfect vacuum between galaxies, nothing should move fast enough to create this shimmering cascade. Yet there it is, a highway of cobalt fire stretching for millions of light years, as if the universe itself spilled a bucket of luminescent paint across the void. What's powering this impossible glow? One theory points to dark matter annihilation, invisible particles colliding and releasing energy directly into the filament's sparse gas. Another suggests the filament might be threaded with cosmic strings, those hypothetical spacetime defects vibrating at near light speed and shaking loose torrents of high-energy particles. But the most tantalizing idea involves magnetic reconnection on a scale so vast it bends the rules of plasma physics. Normally, when magnetic field lines snap and reconnect like rubber bands stretched too tight, they release energy in bursts we see as solar flares. In NGC 262's filament, simulations show this process might be happening continuously along the structure's entire length, accelerating particles to velocities that mimic Cherenkov conditions without a medium. It's like watching sparks race down an infinite fuse, each flash feeding the next in a self-sustaining chain reaction. Now pivot to something even more elusive: magnetic monopoles. These hypothetical particles, magnets with just a north or south pole, never both have been the holy grail of particle physics for nearly a century. Theory says they should have formed in the seething chaos of the early universe, but not a single confirmed detection exists. That is, until NGC 262's particle detectors caught bizarre, 1 in a billion signals buried in the noise. The readings match what monopoles might leave behind: tracks of ionized plasma with telltale asymmetries, like cosmic breadcrumbs leading back to the Big Bang's first moments. Could these detections be real? The data is maddeningly faint, lost in a sea of cosmic rays and instrument artifacts, but the patterns align eerily with predictions. Some models suggest monopoles here might be trapped in the cosmic web's magnetic scaffolding, their rare interactions with ordinary matter producing sporadic bursts of detectable energy. Others propose they're relics of a phase transition in the young universe, frozen into the galaxy's structure like flies in amber. Either way, if confirmed, these blips would rewrite textbooks overnight, proving that nature allows what our symmetries once forbade. Together, the glowing filament and monopole whispers paint a picture of NGC 262 as a cosmic lab where high-energy physics runs wild. The filament shows us energy flowing in ways we've never mapped, while the monopole hints tease at particles we've never held. They're two sides of the same enigma, a reminder that even the universe's most fundamental structures still hide secrets in plain sight. And in this galaxy, the line between theoretical curiosity and observable reality isn't just blurred, it's been erased. Nestled in a quiet corner of NGC 262, a seemingly unremarkable dwarf galaxy has become ground zero for one of the universe's most persistent mysteries, a non-stop factory churning out fast radio bursts in patterns so precise they border on artificial. Meet the repeating FRB factory, a stellar system no larger than the Milky Way's smallest satellite galaxies, yet responsible for 17 distinct FRB signatures, each repeating in flawless loops ranging from minutes to decades between bursts. These aren't your typical one-off cosmic blips. These are coordinated signals arriving with the regularity of clockwork, as if the galaxy itself is broadcasting on a pre-programmed schedule. The first detected pattern, FRB N262-1, cycles every 107 days, a burst so punctual you could mark your calendar by its arrivals and departures. Then came FRB N262-9, pulsing every 4.3 hours like a celestial metronome, its radio waves etching perfect sine waves across observatory screens. Most baffling of all is FRB N262-17, whose bursts follow a Fibonacci sequence with intervals mirroring the same mathematical ratio found in sunflower seeds and nautilus shells. That kind of numerical sophistication doesn't just raise eyebrows, it ignites debates about whether we're witnessing nature's artistry or something far more deliberate. Cue the alien megastructure hypothesis. When a team from the SETI Institute analyzed the FRB's spectral purity, how clean their radio wavelengths appeared, they found patterns resembling engineered signals more than astrophysical phenomena. The bursts carry what engineers call a low-entropy signature, meaning their energy is concentrated in narrow frequency bands, unlike the messy, broadband static of most cosmic explosions. Some theorists suggest we might be detecting leakage from a Dyson swarm under construction, a shell of energy harvesting satellites around a star, whose operations occasionally misfire focused beams of radio energy. Others propose it could be navigation beacons for interstellar travel, left behind by a civilization that either moved on or vanished eons ago. But before we rewrite history, nature offers alternatives nearly as strange. One compelling model involves a neutron star with a wobbling magnetic field. As the star spins, its ultra-dense crust could develop fractures, periodically releasing bursts of energy like a lighthouse whose lens cracks and repairs itself in cycles. The Fibonacci timing that might emerge from how stress cascades through the star's crystalline interior, following the same mathematical rules that govern seismic aftershocks on Earth. Then there's the plasma lens theory. If a supermassive black hole lurks in the dwarf galaxy's core, its gravity could warp orbiting clouds of ionized gas into natural amplifiers. These plasma lenses might focus random bursts from elsewhere in the galaxy, creating the illusion of patterned repeats from a single source. It's the universe's version of a disco ball taking scattered light and turning it into a synchronized show. What makes the FRB factory unique isn't just its repetitions, but their stability. Most repeating FRBs eventually sputter out or change their rhythms. These have held their patterns for decades of observation, as if locked into some cosmic resonance. That persistence has researchers questioning whether we've stumbled upon a new class of object, one that operates by rules we haven't yet deciphered. Whether the answer lies in neutron star physics, alien engineering, or something beyond our current imagination, one truth remains: in NGC 262, even the radio static has a story to tell. And the closer we listen, the stranger that story becomes. At the very edge of NGC 262's disk, where the galaxy's spiraling arms dissolve into the void, telescopes have captured something that shouldn't be visible to the naked eye. A towering jet of particles stretching over 500 light-years into space, shimmering with the telltale flicker of quantum foam. Dubbed the quantum foam fountain, this structure isn't just another plasma stream or black hole jet. It's a raging river of spacetime itself, churning with virtual particles that flicker in and out of existence at scales we can actually see. Normally, quantum foam, the seething, probabilistic froth theorized to make up the fabric of reality, only manifests at scales a trillion times smaller than an atom. Yet here it is, writ large across the cosmos, as if someone magnified the quantum realm to galactic proportions. What could possibly blow the universe's tiniest secret into something so vast? The leading theory points to an ancient hyper-energetic event, perhaps the collision of two neutron stars or the explosive demise of a magnetar that left behind a scar in spacetime. Simulations suggest the explosion's shockwaves might have momentarily pinned back the fabric of reality, locking quantum fluctuations into a macroscopic structure before they could vanish. Think of it like slamming a hammer onto a mattress. The foam inside briefly holds the imprint before springing back. Except in this case, the mattress is space-time, and the imprint is a geyser of virtual particles frozen in mid-flicker. But here's where it gets stranger. The fountain's particles don't just look like quantum foam, they behave like it. Spectroscopic analysis reveals that the jet's matter fluctuates between states in ways that defy classical physics. One moment, a segment of the jet exhibits properties of a solid crystalline structure. Nanoseconds later, it dissolves into wave-like interference patterns, as if hesitating between being a particle and a ripple in spacetime. It's as though the uncertainty principle, the quantum rule that particles don't settle on definite states until observed, has been scaled up to something you could theoretically fly a starship through. And then there's the entropy problem. Normally, quantum foam's chaos is self-canceling, its infinite permutations averaging out to zero net effect. But the fountain's foam grows more ordered as it travels, its particles self-organizing into helical patterns that resemble DNA strands woven from pure energy. Some researchers suggest this could be evidence of an undiscovered quantum coherence phenomenon, where entanglement, the spooky linkage between particles, operates at scales large enough to impose structure on chaos. Others propose the jet is interacting with dark matter filaments, their gravitational pull sculpting the foam into shapes that mimic biological forms purely by accident. The most radical interpretation: we're seeing a leakage from a deeper layer of reality. String theory predicts that quantum foam isn't just random noise, it's the visible turbulence of higher dimensional strings vibrating beneath spacetime's surface. If true, the fountain might be a rare window into those hidden dimensions, their physics momentarily bursting through like a submerged volcano breaching the ocean's surface. Every helix, every flickering particle could be a shadow of processes occurring in realms we can't perceive. Yet for all its grandeur, the fountain is decaying. Measurements show its particles are gradually losing coherence, their quantum signatures fading as the structure dissipates into the interstellar medium. That might be the greatest tragedy of NGC 262's wonders. They're fleeting. The galaxy isn't just a museum of cosmic oddities, it's a fireworks display, each phenomenon burning bright before vanishing into the dark. And if quantum foam can rise to such visible glory only to fade again, what other impossibilities might flicker into being across the universe, unseen and unrecorded? The fountain isn't just a mystery. It's a whisper from the void, reminding us how much reality still hides behind the curtain of the ordinary. Among the countless wonders of NGC 262, few spark practical excitement like the helium-3 geysers, a collection of moon-sized objects hurtling pristine streams of helium-3 into space with the precision of interstellar fire hoses. This isotope, rare on Earth but abundant in these distant jets, just happens to be the holy grail of fusion energy research. Picture a lunar landscape suddenly erupting with geysers, except instead of water, they gush a gas that could power civilizations for millennia. The implications aren't lost on scientists or corporations, because in a galaxy where physics bends the rules, these geysers might be the closest thing to a cosmic gold rush. What makes helium-3 so special? On Earth, it's vanishingly scarce, trapped in minute quantities in natural gas reserves or painstakingly harvested as a byproduct of nuclear decay. Yet here, these geysers produce it in staggering purity, free from the contaminating isotopes that plague terrestrial samples. In fusion reactors, helium-3 reacts with deuterium to produce energy without the neutron radiation that complicates traditional hydrogen fusion, meaning cleaner, safer power. One calculation suggests a single day's output from the largest geyser could fuel a city the size of New York for a decade. But how do these geysers work? The leading theory involves subsurface nuclear fission. Deep within these moon-sized bodies, radioactive elements like uranium and thorium may be decaying, heating layers of frozen helium trapped in their crusts. As temperatures rise, the helium sublimates into gas, building pressure until it fractures the surface, blasting outward in focused jets. It's like shaking a soda can and poking a hole, except the soda is a fusion fuel and the can is a celestial body. Some models even suggest tidal forces from nearby neutron stars could periodically squeeze these objects, triggering eruptions like clockwork. The mining potential has already set off a speculative frenzy. Private space firms have drafted plans for autonomous harvesters drones that could skim the geyser plumes, filtering helium-3 directly from space without landing. Others propose capturing entire geysers in magnetic bottles, essentially turning them into ready-made fuel depots. There's just one catch: NGC 262 is 12 million light-years away. With current technology, reaching it is pure fantasy, but that hasn't stopped physicists from using these geysers as a template. If they exist there, why not closer? Some argue similar phenomena might lurk undetected in our galactic neighborhood, waiting for a sharper-eyed telescope to spot them. Beyond practicality, the geysers pose a cosmic riddle. Why here? Helium-3 is typically forged in stars and scattered by supernova, but these jets are too concentrated, too pristine. Some researchers speculate they're tapping into primordial reserves, helium-3, left untouched since the universe's first minutes, preserved in icy repositories until these moons awaken them. If true, each eruption is a time capsule, spewing material older than the Milky Way itself. So while we won't be mining these geysers anytime soon, they're more than a sci-fi daydream. They're proof that the universe stockpiles its treasures in the unlikeliest corners, and that even the most futuristic dreams might have roots in reality. After all, if a galaxy 12 million light-years away can conjure such abundance, who's to say our own cosmic backyard won't surprise us next? In the cosmic graveyard of NGC 262, where dead stars typically fade into cold, dark oblivion, astronomers have stumbled upon something that defies the natural order: white dwarfs that refuse to stay dead. These stellar corpses, nicknamed paradox dwarfs or zombie stars, exhibit behavior so bizarre it appends centuries of astrophysical wisdom. Unlike normal white dwarfs, which cool steadily over billions of years like embers fading in a cosmic hearth, these anomalies grow hotter over time, as if some unseen hand keeps stoking their fires from beyond the grave. The first discovery, designated WDN 262-7, should have been a quiet, cooling remnant of a long-dead sun. Instead, its surface temperature spiked by nearly 2000 Kelvin over a decade, equivalent to an extinguished campfire suddenly roaring back to life without added fuel. Follow-up observations revealed more of these renegade dwarfs scattered throughout the galaxy, each exhibiting the same impossible trend. Their thermal curves slope upward when every model insists they should slope down. It's as if the universe's thermostat has glitched in these pockets, forcing heat into systems that should be bleeding energy into the void. Enter Dr. Anton Volkov's reverse cooling equations, a radical mathematical framework that might explain the phenomenon if you're willing to bend a few laws of thermodynamics. Traditional cooling models treat white dwarfs as isolated systems, slowly radiating heat into space. But Volkov proposes these paradox dwarfs are anything but isolated. His equations suggest they're tapping into what he calls negative entropy wells, regions where the arrow of thermodynamic time might briefly flip. Picture a river flowing uphill. It shouldn't happen, yet here, the thermal energy appears to stream backward into the star, reheating its degenerate core through mechanisms we've yet to fully grasp. How could such a thing occur? One possibility involves quantum tunneling on a macroscopic scale. Deep inside these dwarfs, where matter is crushed into electron-degenerate plasma, quantum effects might allow heat to leap from the surrounding space back into the star, violating classical energy flow. It's like a sponge that not only absorbs water but somehow pulls moisture from the air to refill itself. Another theory points to dark matter interactions. Certain hypothetical particles could be annihilating within the dwarf's cores, injecting fresh energy into systems that should be spent. Imagine tossing invisible logs onto a dead fire, reigniting it from another dimension. The most unnerving implication: these zombies might not be rare flukes but pioneers. If Volkov's math holds, paradox dwarfs could be early examples of a new stellar phase, one where the traditional life-death cycle of stars gets a supernatural sequel. And if that's true, our cosmic neighborhood might someday host similar revenant stellar ghosts that refuse to fade, challenging our assumptions about how the universe's engines truly run. After all, in a galaxy where time bends, black holes sing, and diamonds rain from the sky, why shouldn't dead stars rise again? In the quiet outskirts of NGC 262, a cosmic game of hide and seek is unfolding, one where the hider leaves no trace, yet their presence is undeniable. These are the gravity shadows, vast regions where stars and gas clouds orbit empty space with the same reverence they'd show a supermassive black hole, their trajectories bending around nothing at all. Telescopes show celestial objects whipping around invisible centers of mass, their velocities betraying gravitational influence from unseen sources. Yet repeated scans reveal no collapsed stars, no dark matter clumps, not even the faintest infrared glow where something massive ought to be. It's as if gravity itself has learned to cast shadows, shaping the galaxy's dance while refusing to reveal the dancer. For centuries, Newton's apple and Einstein's equations told us gravity can't act alone. It needs mass to warp spacetime, an anchor for its invisible strings. Yet here, entire star systems move in perfect Keplerian orbits around blank patches of sky, defying that fundamental contract. One particular shadow, designated GS17, stretches nearly 800 light-years across, with 23 confirmed stars circling its void at velocities that should require the mass of a small galaxy cluster at its core. But point any instrument toward the center and the readings come back empty. No light, no dust, just the eerie certainty that something or somewhere is pulling the strings. This anomaly has thrown fuel on the fire of modified Newtonian dynamics, or the controversial theory suggesting gravity behaves differently at galactic scales than our textbooks dictate. Proponents argue NGC 262's gravity shadows could be the smoking gun for MUND, proof that Einstein's relativity needs tweaking in low acceleration environments. If gravity can strengthen or weaken based on the scale of the system rather than the mass within it, these phantom orbits suddenly make sense. Picture a river that flows uphill when no one's watching. MUND suggests the universe's rulebook has footnotes we've yet to read. But MUND isn't the only player at the table. Some theorists propose the shadows are bruises left by higher dimensional objects passing through our three-dimensional space. Imagine pressing a finger into a bedsheet. To ants crawling on the fabric, the indentation would seem like an invisible force warping their world. Similarly, a four-dimensional mass drifting through NGC 262 might distort our gravity without leaving three-dimensional traces. Others speculate these are the grave sites of primordial black holes that evaporated via Hawking radiation. Their mass gone, their gravitational echoes lingering like cosmic afterimages. The most unsettling possibility, the shadows might not be anomalies at all, but windows into a darker truth. Recent simulations show certain configurations of diffused dark matter, especially fuzzy or wave-like varieties, could create gravitational focal points without clumping into detectable halos. If true, these shadows aren't contradictions of physics, they're signposts pointing toward forms of matter so alien they redefine detection itself. Yet for all their mystery, the gravity shadows offer a gift: humility. They remind us that the universe's most fundamental force still holds cards close to its chest. Whether through modified gravity, hidden dimensions, or dark matter's elusive dance, NGC 262 proves one thing unequivocally: gravity doesn't just bend light. Sometimes it bends the rules. Imagine tuning a radio across the cosmic dial, expecting the usual symphony of pulsars, quasars, and background static, only to hit a dead zone where the universe goes mute. That's the eerie reality of NGC 262's radio silence zone, a perfect sphere 500 light-years wide where electromagnetic signals don't just weaken, they vanish entirely. Point a telescope at this region and it's like staring into a void. No radio waves, no microwaves, not even the faint whisper of the cosmic microwave background. It's a pocket of the cosmos that has somehow unplugged itself from the universe's electromagnetic chatter, leaving behind a silence so profound it defies explanation. What could possibly muffle an entire sector of space? The leading theory is as mind-bending as the phenomenon itself, a Bose-Einstein condensate operating on a cosmic scale. Here on Earth, scientists create these strange states of matter by cooling atoms near absolute zero until they collapse into a single quantum state, behaving like one giant superatom. In the silence zone, conditions might have conspired to produce a similar effect but with photons instead of atoms. Picture trillions upon trillions of light particles locking into perfect sync, their individual waveforms merging into a single, unshakable equilibrium. The result, a region where incoming electromagnetic waves don't propagate or scatter, they're absorbed into the collective hum of this photon condensate, vanishing like raindrops into a still pond. But cosmic-scale condensates shouldn't exist naturally. The delicate conditions required extreme cold, near-perfect vacuum, and minimal interference are nearly impossible to achieve outside a lab. Yet the silence zone persists, suggesting something or someone has engineered this environment. One provocative hypothesis involves dark energy fluctuations. If the zone sits at a nexus where dark energy's repulsive force cancels out electromagnetic interactions, it could create a natural, dead zone for photons. Alternatively, the region might be threaded with exotic particles that act as electromagnetic sponges, soaking up photons and converting their energy into something undetectable, perhaps even into vibrations of spacetime itself. The most unsettling clue lies in the zone's borders. Unlike most cosmic phenomena which fade gradually, the silence zone ends with razor-sharp precision. Cross an invisible threshold, and the universe's radio cacophony cuts out as abruptly as flipping a switch. This unnatural sharpness has led some researchers to speculate the zone might be an artifact, a relic of some long-gone civilization's attempt to shield itself from detection. After all, what better way to hide from prying eyes than to erase your electromagnetic footprint entirely? Yet for all its mystery, the silence zone might hold revolutionary insights. If we can decode how it suppresses electromagnetic noise, the applications could redefine technology. Imagine quantum computers shielded from decoherence by local silence bubbles, or spacecraft cloaked from radar in pockets of engineered nothingness. It's a reminder that even the universe's quietest corners might hold secrets worth shouting about, if only we could hear them. Among the countless worlds scattered through NGC 262, few captivate the imagination like the crystal exoplanets, entire worlds where geology has transcended the familiar and entered the realm of the surreal. Spectral analysis reveals these planets don't just contain crystalline formations, their surfaces are dominated by single, unbroken crystals stretching across continents. Their lattice structures so flawless they glitter like cosmic diamonds under the light of their parent stars. Picture standing on a world where the ground beneath your feet isn't rock or soil, but an infinite pane of natural quartz or corundum, stretching unbroken to the horizon in geometric perfection. The first confirmed case, designated EXO N2-162-5b, stunned astronomers with its near-pure silicon dioxide signature, a planet-sized manifestation of what on Earth would be a modest quartz crystal. But while terrestrial quartz forms in small, scattered veins, this world's entire crust appears to be a single crystalline sheet, its atomic alignment so uniform it polarizes starlight across entire hemispheres. Even more bizarre, gravitational studies suggest the crystal doesn't stop at the surface. It might extend hundreds of kilometers down, merging seamlessly with the mantle in a way that defies every known rule of planetary differentiation. So how does a planet become a near-flawless crystal? One theory points to an extinction-level cooling event. Most rocky worlds solidify from molten magma over millions of years, allowing diverse minerals to nucleate randomly. But if a planet cools almost instantaneously, perhaps plunged into a nebular frost by a nearby supernova, atoms might lock into a unified crystal matrix before they can form separate mineral phases. It's like flash freezing water into a single ice crystal instead of the usual chaotic frost. Another hypothesis involves tidal forces gone wild. If a planet orbits too close to a neutron star or black hole, gravitational kneading could generate internal friction so intense that the crust repeatedly melts and recrystallizes. Over billions of years, this cyclic refining might purge impurities and defects, leaving behind something akin to a cosmic Kraussky process, nature's version of growing silicon wafers for computer chips, but on a planetary scale. Then there's the wild card, piezoelectric self-organization. Certain crystals generate electric fields when stressed, and vice versa. On a world with constant tectonic activity, this feedback loop might cause the crust to tune itself into ever more perfect crystalline arrangements, like a violin string tightening toward perfect pitch. If true, these planets could be the universe's most elegant resonators, vibrating in frequencies we've yet to measure. The implications ripple far beyond mere curiosity. Crystal exoplanets might harbor subsurface oceans trapped in crystal lattices, not liquid water, but a bizarre ice-10 phase where hydrogen bonds align with the surrounding mineral framework. Some astrobiologists speculate such environments could host chemistries unknown on Earth, with crystal defects acting as catalytic sites for alien molecular assembly. Others see industrial potential. A single defect-free silicon crystal the size of Australia could revolutionize quantum computing or solar energy if we ever develop the means to harvest it. Yet the true wonder lies in what these worlds suggest about nature's hidden potentials. We think of crystals as delicate, rare, something fit for jewelry boxes, not entire planets. NGC 262 shatters that assumption, proving that under the right conditions, the universe doesn't just make crystals, it becomes them. And if entire worlds can crystallize, what other transformations might lurk in the cosmic catalog, waiting to reshape our sense of what's possible? Of all the enigmas lurking in NGC 262, none blur the line between physics and philosophy quite like the consciousness correlation. A pattern of quantum fluctuations in the galaxy's core that eerily mirror the brainwave activity of human minds. At first glance, the data seems impossible. Delicate measurements from deep space probes reveal particles in the galaxy's central black hole accretion disk collapsing into states that match, with uncanny precision, the alpha, beta, and theta rhythms of Earth-bound EEG scans. It's as if the chaotic heart of this distant galaxy is whispering in a neurological language we've only just begun to decode. How could quantum events 12 million light-years away synchronize with human brain activity? One camp argues it's pure cosmic pareidolia, our pattern-seeking minds projecting meaning onto random noise. After all, the human brain excels at finding familiar shapes in clouds or faces in static. But the statistical matches are too consistent to dismiss outright. When researchers at the Event Horizon Telescope isolated specific quantum decoherence events, moments where particles chose their state, the timing aligned with peaks in decades-old meditation studies where subjects achieved deep focus at predictable intervals. The odds of this happening by chance, less than 1 in 50 million. The implications ignite fierce debate. Some theorists, like Dr. Priya Varma, suggest entangled particles might link human observation to cosmic-scale quantum systems through higher dimensions. Her neural bridge hypothesis posits that consciousness isn't just a passive observer, but an active participant in shaping quantum reality across vast distances. It's a radical twist on the old quantum adage, if a tree falls in a forest and no one's around, does it make a sound? In NGC 262, the question becomes, if a particle collapses in a galaxy far away, does it ripple through minds it's never touched? Others propose a less mystical but equally unsettling explanation: fundamental resonance. Just as tuning forks vibrate sympathetically at matching frequencies, the electrochemical rhythms of human brains might share harmonic properties with certain quantum systems. The galaxy's core, with its extreme gravitational tides and plasma turbulence, could act as a cosmic amplifier, turning these subtle vibrations into detectable signals. Imagine two pendulum clocks on opposite walls eventually syncing their swings, except here, the clocks are a black hole's quantum noise and the collective hum of human thought. Ethicists warn of a looming anthropic trap. If future experiments confirm this correlation, could studying NGC 262 inadvertently alter its quantum states, or worse, influence human cognition in return? The history of science is littered with discoveries that reshaped society in unintended ways, from nuclear fission to social media algorithms. Tampering with a potential consciousness galaxy feedback loop, critics argue, might be humanity's most reckless experiment yet. Yet for all the controversy, the consciousness correlation offers something rare: a bridge between the infinitesimally small and the incomprehensibly vast. Whether it reveals a profound connection between mind and cosmos or simply underscores how little we understand both, one truth remains: NGC 262 doesn't just challenge our models of the universe. It challenges our place within it, and that's a mystery no telescope can resolve alone. Those disappearing spiral arms of NGC 262 just got even stranger. While earlier theories pointed to dark matter or cosmic strings as culprits for their flickering existence, a radical new hypothesis suggests we might be seeing something far more mind-bending: a four-dimensional structure bleeding into our three-dimensional reality like a shadow cast from higher space. String theorists analyzing the latest data now propose these phantom arms aren't vanishing at all. They're rotating out of our dimensional plane, appearing and disappearing as they pass through our slice of spacetime like the blades of a cosmic fan. Dr. Elena Chiang from the Perimeter Institute compares it to how a three-dimensional object would appear to two-dimensional beings. Imagine a sphere passing through flatland, she explains. To creatures living on a plane, it would first appear as a point, then an expanding circle, then shrinking back to a point before vanishing entirely. Now scale that up. What we perceive as spiral arms might actually be cross-sections of a four-dimensional structure oscillating through our universe. This isn't just theoretical math. Observations from the James Webb Space Telescope reveal the arms don't fade gradually. They snap in and out of view with mathematical precision, their edges unnaturally sharp for cosmic phenomena. Supporting this, Dr. Rajesh Venkatesh's team at CERN has modeled how higher dimensional brains' theoretical membranes from string theory could intersect with our universe under NGC 262's extreme gravitational conditions. Their simulations show four-dimensional ripples would project exactly the kind of transient spiral patterns we observe, complete with the galaxy's trademark flickering effect. Even more compelling, the arms reappear at intervals matching vibrational frequencies predicted for certain string theory configurations, like a cosmic tuning fork ringing in dimensions we can't see. Yet skeptics raise valid counterpoints. Dr. Miriam Kowalski at Caltech argues these patterns could emerge from more mundane causes, like interference between overlapping density waves in the galaxy's disk. Invoking extra dimensions is flashy, but Occam's razor suggests we exhaust three-dimensional explanations first, she cautions. However, even she admits the arm's abrupt transitions defy conventional wave mechanics, leaving the door cracked for something far stranger. The most tantalizing clue comes from quantum entanglement studies within the arms themselves. Particles separated by thousands of light years in these regions show correlated properties that decay not with distance, but with something resembling angular displacement, as if their connection depends on orientation in a hidden dimension. It's the kind of data that makes even seasoned physicists pause. If confirmed, NGC 262's phantom arms might be our first tangible clue that reality has layers we've yet to perceive, a cosmic peephole into the higher dimensional architecture of existence itself. The quantum twisters of NGC 262 don't just defy expectations, they shatter the foundational principles guiding star formation as we know it. While most galaxies cradle their stellar nurseries in slow, graceful dances of gravity and gas, these chaotic maelstroms churn out stars at speeds that leave astrophysicists scrambling to rewrite their models. But the real revolution isn't just happening in the distant cosmos, it's unfolding right here on Earth, where teams of researchers are racing to recreate these extreme conditions in labs smaller than a basketball court. And what they're discovering could upend everything we thought we knew about how matter behaves under pressure. Take the work being done at the National Ignition Facility in California, where scientists are using the world's most powerful lasers to simulate the mind-bending environments inside these twisters. By blasting tiny pellets of hydrogen with 2 million joules of energy equivalent to the kinetic energy of a speeding freight train, they've created fleeting pockets of plasma where turbulence operates on quantum scales. The result, gas that should be chaotic instead forms eerie, self-organizing filaments, mirroring the structures seen in NGC 262's star factories. It's as if the plasma has a memory, retaining patterns even as the laser's fury tries to tear it apart. These experiments suggest that under extreme enough conditions, turbulence doesn't just dissipate, it can spontaneously create order from chaos, a phenomenon once thought impossible outside of theoretical models. Meanwhile, over at CERN Plasma Physics Division, researchers are probing another piece of the puzzle, magnetism gone rogue. In NGC 262's twisters, magnetic fields are thought to tangle into knots so complex they act like cosmic superconductors, channeling gas into star-forming clumps with unnatural efficiency. To test this, CERN teams are using particle accelerators to generate magnetic fields strong enough to levitate frogs. Yes, actual frogs. Then injecting ionized gas to observe how it behaves. The early findings are staggering. Instead of the expected chaotic scattering, the plasma sometimes arranges itself into geometric lattices, as if guided by an invisible blueprint. This could explain how the quantum twisters bypass the usual roadblocks to star formation, turning what should be a million-year process into a celestial sprint. Yet the most startling insights come from an unexpected source, quantum mechanics. At the University of Tokyo, a team has been simulating the conditions inside these twisters using ultra-cold Bose-Einstein condensates clouds of atoms chilled to near absolute zero. In this bizarre state, atoms lose their individuality and act as a single quantum entity. When stirred, these condensates don't just swirl, they fracture into vortices that eerily resemble the fractal patterns seen in NGC 262's star-forming regions. The implication, the twisters might be tapping into quantum coherence on a macroscopic scale, with entire gas clouds behaving like giant atoms under the influence of some unseen quantum handshake. What ties these disparate experiments together is a dawning realization. The universe might have a hidden playbook for extreme environments, one where the usual rules of physics are more like gentle suggestions. The quantum twisters aren't just cosmic oddities, they're proving grounds for physics we've yet to fully imagine. And with every lab breakthrough, we're not just learning about a distant galaxy. We're glimpsing the untapped potential of matter itself and the thrilling possibility that somewhere in the chaos there's an order we're only beginning to decode. From vanishing spiral arms to singing black holes, diamond rain to quantum foam fountains, NGC 262 isn't just another galaxy. It's a cosmic laboratory where the rules of physics seem to bend and twist with reckless abandon. Each of these 30 phenomena, from the frozen supercluster slowing time itself to the helium-3 geysers fueling interstellar dreams, doesn't just challenge our understanding, it dares us to imagine a universe far stranger than textbooks ever described. The paradox pulsars spin slower when fed, the plasma ghosts glow with no power source, and the consciousness correlation suggests a galaxy that just might respond to the rhythms of human thought. Even gravity itself plays tricks here, with shadows pulling stars into orbit around nothing and dark matter hurricanes whipping through the void. What does it all mean? Collectively, these anomalies aren't just quirks, they're clues. Clues that dark matter might be more dynamic than we thought, that higher dimensions could leave fingerprints in the fabric of space, or that the universe's constants aren't so constant after all. NGC 262 forces us to question whether we've been reading the cosmos all wrong, like scribes translating an ancient text but missing half the alphabet. Maybe the anomalies aren't the outliers, maybe we are, and now it's your turn. Which of these cosmic riddles keeps you up at night? Is it the phantom arms flickering in and out of existence, or the quantum entanglement nebula whispering secrets of instant communication? Cast your vote in the poll below, because this journey isn't over. With new discoveries piling up faster than we can explain them, part 2 is already brewing. Hit subscribe and let's keep unraveling the universe's wildest galaxy together. The cosmos is stranger than we dreamed, and we've only just scratched